Okay, multivariable calculus. This is the moment we've been waiting for. We're going to actually introduce what it means to take a derivative. Here we are. We're in our 6th week of school. And in calculus, we've yet to actually take a derivative. What does it mean? And here's our learning target, of course. Partial derivatives. To take derivatives, guys, we're going to have to focus on a derivative with respect to x or with respect to y. So the first thing here, the partial derivative with respect to x at a given point, I'll tell you what's going to happen. It means take the derivative with respect to x, but here's the trick. Treat y as a constant. That's the name of the game. So, look, we're going to say the partial derivative with respect to x, what does it look like? Well, you're going to have this little delta right here. Almost looks like a backward 6. Partial f with respect to x, you can have a little bar here and say x naught comma y naught. That means the exact same thing as saying dx of f of x comma y, or actually f of x comma y naught, because y is really held constant right there. And then we could say, let's go ahead and let x equal some individual x value. Could we even come up with a limit definition? Yeah, we could. We could say the limit as h goes to 0 of f of x naught plus h comma y naught minus f of x naught comma y naught all over h. What's the name of the game? In all of these scenarios, y is thought of as just an ordinary constant, a number like 7, something like that. Notation, wow, this is super important. Way more notation here than what we had in Calc BC. First of all, look at this, f subscript x. If you see that, f with the subscript of x, it's saying take the partial derivative with respect to x. What else could we see? Well, so very often we'll see z as a function. You might say z with a subscript of x. Wow, you're going to see this little curvy differential right here with delta, z with respect to x. Here's something that's funny, f subscript 1. When you say f subscript 1, you're saying take the derivative with respect to x. You could also say, pardon me, capital D subscript 1 of f. You could also say capital D subscript x of f. All of those, my goodness, I guess I've copied down 6 things right there. Those are all synonymous to say take the derivative with respect to x, just pretend y was a constant. Okay? Well, you might say, well, let me take a guess. To take the partial derivative with respect to y, that means take the derivative with respect to y, but we're going to treat x as a constant. Right? So that's not so bad. Guys, you're going to see that there is a definite parallel down below. We could say, look, it's like recopying what I saw up here. You could say partial f with respect to y. You could say, hey, plug in an x naught comma y naught. Say, hey, that's the same thing as saying d dy of f of, and now you're going to say it's x that is thought of to be a constant, but you'd say let y equal a y naught. And you could say, could you come up with a limit? Yeah. Say the limit is h goes to 0, and this time we'd say f of x naught comma y naught plus h. It's y naught that is changing just a little bit. And you can see it's pretty much just recopying what I did up on top. but just making some quick adjustments. So we can take a look at notation. I bet you right now you have a very good clue as to what those notations would look like. F with a subscript of y. Z with a subscript of y. You could say partial z, partial y right here. F sub 2. If you ever see that, f sub 2, it means take the derivative of f with respect to y. You could say capital D subscript 2 of f. Capital D subscript y of f. All 6 of these are really communicating the same exact thing. They're saying take the derivative with respect to y, hold x as a constant. Now, in your book, on page 927, there's a nice little picture that, more or less showcases what's happening. You've got this surface, you've got this curve. It's almost like a blanket, like a big blanket that's been puffed up with air, and it's up there. And you could say, look, here's a point that we've got in question. What if we made our y value always be the same? That would be like C2. C1. I am so sorry, I misspoke. You can see visually that if y was constant on the y-axis, we'd get something that would look like this C1. And it's kind of like highlighted in yellow here. We could come up with a tangent line to that curve at a point designated on that flat surface, or that curved space, I should say. Likewise, with C2, you can say, well, C2, you could say, well, that's like where x is always going to be the same value. Almost like put a little plane going through a specific x value. C2 would be a curve going through a point A, B, C. And you could see that if you made a tangent line, that's T2 right here. That would be a tangent line to that curve. Well, really, that's what your partial derivative with respect to y would be. You're saying just hold x constant. Let's look at what's happening there. And we'll get a lot more into the geometrical ideas happening in just a little bit. Tell you what, let's get into the mechanics of taking some derivatives and see what it looks like, okay? So here's a function, and it's x squared plus 3xy plus y minus 1. And they're saying, hey, find the partial derivative of f with respect to x at this specific point. Let's just find that derivative first. Almost like making a backward 6 right here. Partial f over partial x. What would that derivative look like? Help me out. What do you think? 2x, then what? Plus 3y, because y is thought to be just some constant, right? It's not going to go away, but the derivative of x just disappears to be a 1. Anything else? No, that's it. And they'd say, no, wait a minute. I've got to plug in a 4, 5. Well, what's going to happen? That's 2 times 4 plus 3 times 5. That's 8 plus 15, and that's 23. Kids might say, well, what exactly did you just find? That was like that yellow tangent line in that picture up above. That's the slope of it, right? That's another way to look at it. You could say, what if I did a partial derivative of f with respect to y? Well, what's the derivative of x squared with respect to y? 0. It's a constant, right? And then you'd say, well, what's the derivative of 3xy if I'm thinking of x as a constant? 3x. What's the derivative of y? A 1, and the derivative of negative 1 goes away. Hey, all of a sudden we're taking some derivatives. How about that? Well, then what? Plug in the point 4, 5. There's no y coordinate to even bother with, and that's okay. 3 times 4 is 12, 12 plus 1. You get 13. You doing okay? All right, let's go to page 2. Now, I don't need to tell you, there will be times when life will get a little more complicated, where perhaps product rules, quotient rules, or chain rules are going to come into play. And that's going to be the case, definitely. let's take a look at this next example. We've got f is, y times the sine of xy. And we want to find the partial derivative of f with respect to x. In other words, treat y as if it were just a fixed constant. Pardon me, what do you think we have to do? The chain rule. You see, a function of x is that sine of x comma y. What is the derivative of the sine of x comma y? It's, a y comes out, doesn't it? We're going to have the cosine of that same argument, but then we need to take the derivative of the inside. You call that a y right there, and you still have your y out in front. Of course, you could have just said it's y squared cosine of xy, right? Why did I put the y to the far, far right? Just to remind you it was the chain rule, right? Of course, we don't have to do that. You could, just do it in your head. Are we doing okay so far? Sometimes kids look at that and they'll say, so what about the partial derivative of f with respect to y? Uh-oh. What do we need here? The product rule. The product rule. Because I have a multiplication of two functions involving y. I've got my u, I've got my v. So you guys remember it's a u v prime. So I'm going to write y. And what's the derivative of sine of xy with respect to y? What's going to happen there? We're going to have an x come out. Yep. Then what? Cosine of xy. In other words, we did the chain rule on that inside. The derivative of xy, if x is a constant, but y is our variable, that's just an x coming out then. Okay, but we're not done. We've got to say u prime v. What's the derivative of u, that y, with respect to y? It's just 1. Usually kids will say, oh, that's not so bad. At least I hope you find it's not so bad. Okay, just got to get used to, some things looking a little bit different. And so there's your partial derivative. All right, when we take a look at this next example, look at the notation, guys. This notation, f sub x. We need to keep seeing this because, there's so many different ways that this can be showing up. And, at first glance, kids look at that and they'll say, oh my gosh, I guess we definitely need the quotient rule here. Do we? Do we need the quotient rule? Actually, if you're on your toes, no. You can, don't get me wrong, you definitely can, but there's only one term that involves x in this little expression. It's right there, right? Imagine everything else is thought to be a constant, like a number like 14 or pi or something like that. So I guess what I'm really getting at is, just to get you thinking, imagine that your function was 14 all over pi plus the cosine of x, and I said take the derivative. Would you need the quotient rule? No. What would you do? You'd probably say, well, I can bring this as y plus cosine of x all to the -1. Quotient rule's fine, don't get me wrong. But now if I just do this, I could say bring down that -1, get -2y, and I'll have y plus the cosine of x now raised to the -2. But now I've got to do the chain rule. Remember, I'm taking the derivative of the inside with respect to x. And what will that come out to? Negative sine of x. So, cleaning it up, it's very likely a negative times a negative you would just see as a positive. So it's 2y sine of x. You could bring this other thing down for sure. Write it as a square, right? As we get to f of y, f sub y, can we avoid the quotient rule? No, bummer. Okay, but that's okay. It looks like our video is going to wrap up here, but yeah, you'll use the quotient rule to finish that. And let's remember the quotient rule. U over v low D high minus high D low.